Hi there, this is Lecture 22 on Section 5.8, Antiderivatives. So all semester long, we've been working towards finding the derivatives of functions, and now we're going to spend just a little bit of time going backwards and finding the antiderivative. So in this case, if you have a function little f of x, then we're going to use capital F of x as the notation for going backwards to the antiderivative. And if that's the antiderivative, if you take the derivative of the antiderivative, it should get you back to where you started, right? They're inverse operations if we think a bit about it as working backwards. Now, keep in mind that we spent like months working on finding derivatives, and we've got one day to finish a section on antiderivatives. So we're only going to do the basics here. A lot of undoing or reversing things like product, quotient, chain rule. Those are all strategies from Calc 2, so that comes up there. We're going to focus on basics, things that you just know the antiderivative of. So first of all, there's some special functions that we can find the antiderivative of. So we're going to make a little chart here where you're going to have little f of x, and then its antiderivative capital F of x. And so one of them that we can work with is e to the x. E to the x is its own derivative, so it's also its own antiderivative. So you get e to the x there as well. We can work with sine and cosine, our trig functions. We can't work with ln. The antiderivative of ln requires by parts, so which is a Calc 2 thing, not a Calc 1 thing. The antiderivative of sine, so you're asking what function has as its derivative sine x? Well, that's going to be cosine x, except the derivative of cosine is negative sine, so we need to make it negative. Then what function has as its derivative cosine x? Well, that's sine x. The other four trig functions are going to require other efforts, like what I'm thinking is typically you use substitution to find the antiderivative for the other four trig functions. So we're not going to write those down. But we do know four other trig functions for which we know the antiderivative of. And those are these. So secant squared, that's the derivative of tangent x. So the antiderivative of secant squared is tangent x. Cosecant squared is the derivative of cotangent x, but don't forget that one's got to be negative as well. Then secant x tangent x is the antiderivative for that is secant x, because that's the derivative of secant x. And same thing, cosecant x cotangent x. The antiderivative there is negative cosecant x. So that's our quick list of special functions. Those are the ones we know that we can go backwards from. We also want to be able to undo our power rule. So if we think about our power rule for derivatives, if I had f of x equals x to the fourth, in order to take the derivative, f prime of x, we got 4x cubed by multiplying by the exponent. And then we took the exponent minus 1. So for antiderivative, we're going to think about reversing the process, doing the exact opposite. But then I also have to reverse the order, right? If you think about putting on a shirt and then putting on a sweatshirt, in order to undo that, you have to take off the sweatshirt first. So we have to undo the exponent minus 1 first. So if you think about f of x equals x to the fourth, to find the antiderivative, capital F, I'm going to have to add 1 to the exponent. So my new exponent's going to be 5. So we're going to take our exponent plus 1. And then we're going to divide is the opposite of multiplying. The question is, do I divide by the 4 or the 5? Well, keep in mind that if we were to find the antiderivative, we can check to make sure it's correct by taking the derivative, because we should get back to where we started. So if we think about dividing by the 4, and I take the derivative of that, I'm going to get 5x to the fourth over 4, and the 5 and the 4 won't cancel. So what I want here is not dividing by 4. I want to divide by the new exponent. I want to divide by 5. That way, when I take the derivative of capital F, I get the 5x to the fourth over 5, and the 5's cancel out. So then we're going to divide by the new exponent. Keep in mind that dividing here, this is the same as multiplying by the reciprocal. So if you're working with fractions, that can be useful. So that gives us the following power rule for antiderivatives. Okay, if you have x to the n, what you're doing is increasing the exponent by 1, so you're making it x to the n plus 1, and you're dividing by the new exponent n plus 1. Now, one tiny little thing to remember here is that the n plus 1 is now in the denominator, so this does not work if n is equal to -1, so it doesn't work for that one. We'll have to look at that one in a second. Otherwise, this works for all powers, no matter what the power. If you're working with x equals -1, then you're working with x equals x, function equals x to the -1, and that's 1 over x. And we know that the 1 over x is the derivative of ln x, so it's a special case. Okay. So I could add that one to my special functions list up here. Right? We could add 1 over x gives us the natural log of x. And not only natural log of x, but I'm going to put absolute values around the x. And the reason for that is because you're allowed to plug in negative numbers into 1 over x. So the domain here includes things like -2. But when you take the natural log of that same set of numbers, you take the natural log of -2, that doesn't make any sense. So we need the absolute value there to make sure we can maintain our domain. Okay. So what does we have one last rule here, and that is when you take the derivative of a constant, you lose it. It goes away. So it's possible that your function had a constant in it, right? For example, if you had f of x equals 2x plus 1, and you take the derivative, you just get 2. So when you're trying to find the antiderivative of little f of x, or actually of the f prime of x, if you're trying to go backwards, you're adding on the x to the 2 to get the 2x, but you don't know, if I didn't know that the f of x was 2x plus 1, and I'm trying to find the antiderivative just from here, I wouldn't know that the plus 1 is there. But there's potentially a constant on any function that we don't know is there. So what we do is we add a plus c. Okay. You add a plus c to all antiderivatives because maybe there's a constant there that you're not aware of, okay? Now, you can find that constant if I give you information about the antiderivative. So if I tell you some kind of condition, then you can go back and find the c. I'll show you one of those in the examples, okay? So we're going to add plus c to all antiderivatives. And the notation for that would be something like, if you have little f of x, then capital F of x is equal to the antiderivative of little f plus a constant. Okay. So let's see how that works here. So when we're going to take our antiderivative here for 4x minus 5, we leave the 4. We're going to increase our exponent from 1 to 2 and divide by the 2. For the minus 5, you get a minus 5 by taking off the x, so we're just going to put the x back on. So it's just going to be minus 5x. And then we're going to add a plus c. If you simplify that, that's 2x squared minus 5x plus c. And if you want to check to make sure you did it right, we can say, okay, well, if capital F is 2x squared minus 5x plus c, and I take the derivative of that, I get 4x minus 5, which is indeed what I started with. Okay, so if you take the derivative of your answer, you should always get the original back. All right, let's take a look at number 2. Now look, number 2 also has some additional information, so that's going to allow me to find the value for c. So we find our antiderivative here. This is 2. We increase to 4 and divide by 4. Leave the 4, increase the 2 to 3, divide by 3. The 1/2 doesn't have an x, so let's put 1 on there. And the antiderivative of e to the x is e to the x. And then we want to use this condition that says when I plug in 0, I get 3. So if I plug in 0, the first 3 terms are all gone. But if I plug in 0 to e, I get e to the 0, which is just, sorry, I forgot my plus c. That's why it didn't work. Okay, don't forget your plus c. Plug in 0, then it's e to 0, which is 1, plus your constant. So this is 3 equals 1 plus a constant. Subtract the 1, and that tells me that the constant is 2. And so my antiderivative, in all its glory, is 1/2 x to the 4th minus 4/3 x cubed minus 1/2 x plus e to the x plus 2. Now, don't forget, like in example 3 here, that if you have things like square roots, you're going to have to convert them to powers. If you have x's in the denominator, you're going to have to convert them to powers. So I'm going to think of this as x to the negative 2 plus x to the 1/2 plus cosine x, just as you would if you were doing derivatives. So now when I find the antiderivative, add 1 to the negative 2, that gives me negative 1, and divide by the new exponent. X to the 1/2, add 1, that becomes 3/2. Multiply by the reciprocal, which is 2/3. Antiderivative of cosine x is sine x plus a constant. And before I call that my formal answer, let's get rid of the negative exponent. So this is negative 1 over x plus 2/3 x to the 3/2 plus sine x plus c. And lastly, number 4, we're going to rewrite this one as 3 times 1 over x plus x to the 1/4 minus secant squared. So that when we go ahead and take our antiderivative, I leave the 3. The antiderivative of 1 over x is the natural log of absolute value of x. Then for x to the 1/4, I add 1 to make it 5/4 and multiply by the reciprocal. And then minus secant squared, the antiderivative there is negative tangent x plus a constant.